In this session, I am going to discuss various important theorems about compact set, and we will see various examples based on compact set. So in continuation to that, the first theorem is that every closed subset of a compact set is compact. Already we have seen that a set is said to be compact if every open cover has finite subcover. And to discard that a set is not compact, one need to construct at least one open cover which has no finite subcover. And we have also seen proof of one of the important result, Hein-Borel theorem about compactness. So here the proof, here one of the theorem I am going to discuss. Let me write the statement of this theorem. Every closed subset of a compact set is compact. Every closed subset of a compact set is compact. Every closed subset of a compact set is compact. And this property that a subset A of R is said to, let me write Hein-Borel property. In some book you will find that if every open cover has finite subcover, this property is also called as Hein-Borel property. So let me write a statement of Hein-Borel property. Hein-Borel property that if every cover, a subset A of R of real numbers, set of real numbers is said to have Hein-Borel property, if every open cover of A has a finite subcover. Has a finite subcover. So this property is also called as Hein-Borel property, or in fact this one is the definition of a set to be compact. But here I am going to prove that every closed subset of a compact set is compact. So to do this, its proof, suppose B is subset of A is compact, A is compact and B is closed. It's given as B is closed. Now, if A is compact, then it will satisfy Hein-Borel property, or I can say that every open cover of A must have at least one finite subcover. So now we will prove. Now suppose B, actually we will try, here the idea is that we will try to take open cover for the set B, and then we will extend that open cover to A, and using compactness of A, it must have finite subcover. Then we will show that it will also have finite subcover for the set B. So suppose this family of open set where lambda belongs to indexing set is an open cover for B. So as is an open cover for B. We know that open cover means every member of this set is an open set, and its union is going to cover the set B. So I can write that B is contained into union of B lambda, where lambda belongs to index set. Now, if, for example, this one is A and suppose this one is B, then obviously this one is B complement and B union B complement. If I take B complement on both sides, union with B complement on both sides, then I can write here that B, see, since B is closed, so B complement will be open. So if I take union with B complement where lambda belongs to indexing set. Why B complement is open? Because B is closed. As B is closed, this implies B complement is open. B complement is open. Now here one thing is also actually B complement union B, because here subsets are of R. So I can say that B complement union B is going to be whole R. So I can write here that R set of real number is going to be contained into B complement union of these open sets where lambda belongs to index set. And A is subset of R. As A is subset of R, so this union is going to cover, since this union is going to cover the whole R and A is subset of R, so this is also going to form an open cover for set A. So from here I can write A is contained into B complement union B lambda, where lambda belongs to indexing set. Now observe from here that the family F consisting of B complement and B lambda is an open cover for A. The family here consisting of this B lambda and B complement is going to form an open cover of A, and A is given to be compact. We have assumed that A is compact. So this open cover must have finite subcover. Let me write on the next page. From here we have it's given that A is compact, and B is closed. B is closed. We have reached. I have written this, that A is contained into B complement union of B lambda, where lambda belongs to index set. So since A is compact, so it must have finite subcover. So from this collection, there must exist some finite subcollection including B complement which covers A. So I can write from here that this open cover, this open cover must have a finite subcover. This open cover must have a finite subcover, say B complement and B lambda 1, B lambda 2, B lambda n, which is also going to cover A. So I can write that A is contained into B complement union B lambda 1 union B lambda 2 union B lambda n. But B is contained into A. Look, B is contained into A. So if this is going to cover the set A, it will also form and cover for set B. So I can write here that B is covered by B complement union B lambda 1 union B lambda 2 B lambda n. Now since B is contained into A, now B intersection, if you look at B intersection B complement is 5. B intersection B complement is 5. So I can say that no element of B is present in B complement. So even if I remove B complement from here, then again this remaining open sets will be going to form an open cover for B. So I can say that as no element of B is present in B complement, as no element of B is present in B complement, so this implies that this collection B lambda 1, B lambda 2 is also a cover for B. So we have, since this B lambda, this collection B lambda is arbitrary, and every open cover for B will always have open for this finite sub collection for B. This implies that B is also compact. So here idea is that we started from an open cover of A and adjoining B complement, because B is a closed set, so adjoining B complement we have formed an open cover. If we even adjoin B complement, then it is also going to form A, and B complement is also open because B is closed. From there, because B is contained into A, so if this one is also going to form an open cover for set A, and A is given compact, so it must have finite subcover. So this we have used for finite subcover for A, as A is compact. Now B is contained into A, so this open finite subcollection is also going to contain B, and since B complement has no element common with B, so even after removing, we always have for some finite subcollection from this member which also cover set B. So in this way one can show that every closed subset of a compact set is compact. For example, this B, if I take A is equal to say closed interval 0 1, equal to closed interval 0 1, and B is equal to, let me discuss other case first, other cases.